Thank you for the introduction and welcome everyone. I am Stefan van der Sar from Delft in the Netherlands, and I'm going to talk about X-ray photon counting scintillation detectors, and in particular those based on the lanthanum bromide scintillator and silicon photomultipliers. First of all, X-ray photon counting detectors represent a kind of optimal or ultimate X-ray detector, as they try to measure both the number of photons and the energy of each photon. And that is typically done by counting the number of detector pulses and determining the pulse height as a measure of the energy associated with the photon that caused that pulse. In detector development, there are a few requirements. For example, in medical imaging, stable and reliable performance is very important. The X-ray energies go up to 150 keV, so we need good detection efficiency in that range. And we need very fast response because the fluence rate is very high in most applications. And in something like diagnostic CT, it can even exceed 10 to the power 8 seconds per second per squared millimeter. And if your response is not fast enough, so if you have too long pulses, they start to overlap at high rate, a phenomenon that we call pulse pileup, and that leads to the wrong number or energy of the photons. So for those last two requirements, because of those, many people worked on direct conversion of the X-ray into electric charge in layers of cadmium telluride or cadmium zinc telluride. And this yields very fast pulses, and it allows to have many pulses per squared millimeter, thereby reducing the rate requirement per channel. But you need very high quality material to make this stable and reliable. And you can ask yourself if it will become cost effective. And another issue may be that the number of manufacturers that can produce such high quality material is limited. So there's also an alternative detector concept developed. That one is based on silicon. Silicon is, of course, widely available in high quality, but it has relatively low density and atomic numbers. So you need to adapt this relatively simple detector design. So at the moment, we have two detector concepts with their specific advantages and also challenges. And in Delft, we ask ourselves the question, can we develop another detector concept? And we came up with the silicon photomultiplier or SIPM-based scintillation detector. So in such a detector, an X-ray photon will first be converted to optical photons, and those are detected by a light sensor, which is in our case the SIPM. And the number of photons that is generated is a function of the energy of the X-ray photon, and they don't arrive, let's say, instantaneously after the X-ray interaction at the light sensor, but their arrival times rather follow an exponential distribution characterized by a decay time constant tau d. So this parameter has like a huge influence on the pulse duration. Now, each photon that is in the end detected gives rise to a current pulse, and that's also an exponential decay with decay time constant or recharge time constant, as we call it, tau r. And what's very special about SIPM is that it provides a gain in the order of 1 million. So this pulse contains about 1 million electrons, and that helps to raise the relatively weak scintillation light pulse from a single photon above the noise level of your electronics. And because of the way this works, the total output pulse will be a convolution of both signals, giving rise to a pulse that looks like this, and its height is then related to the photon energy. Now, in this talk, I want to focus on an experimental evaluation of the spectral and count rate performance of a very fast silicon PM-based scintillation detector. The detector that we are going to look at is a single pixel detector based on a 1 by 1 by 3 cube millimeter lanthanum bromide crystal from Saint-Gobain crystals. It has like reasonable density and atomic numbers for X-ray detection, and it's known for a combination of good energy resolution and fast response. So this decay time constant of only 16 nanoseconds. We coupled that detector to a 1 by 1 SIPM, also with a very fast response of 7 nanoseconds. But we did this in a nitrogen environment because lanthanum bromide is a hygroscopic material. So what does it look like? In this picture, you see a few silicon PMs, and on one of them, I glued scintillation crystal, then covered that in white reflective powder to guide the light towards the sensor, and then applied an epoxy sealing, which allows us to bring the detector out of the nitrogen environment and do experiments. And schematically, that looks like this. Then we performed a series of experiments, first using a couple of low-activity radioactive sources, americium, barium, cobalt, in order to study the linearity of the detector response, the energy resolution, and the spectral separation capabilities. Then we moved to an X-ray tube facility, where we performed a tube current sweep in order to investigate the count rate performance. Detector readout was fairly simple. So because of the high gain, you can just convert current to voltage using a transimpedance amplifier without changing the raw pill shape. And then we fed those signals into a digital oscilloscope and did some offline post-processing then. And the most important step in that is the application of a second order low-pass filter. Why is that needed? Well, because of the limited number of scintillation photons in each pulse, you may have these kind of fluctuations, as you can see here, for example. And if you want to determine the number of photons or derive an energy, then this is going to deteriorate your measurement. So we investigated two different cutoff frequencies, namely one of 25 and 100 megahertz. The 25 is most efficient in reducing the variations in pulse height, so it's good for energy resolution, but it also elongates the pulse shape, as you can see here. So from a rate point of view, it's not beneficial, and the 100 megahertz is better able to maintain the original pulse shape. Then we applied two counting algorithms to each pulse strain. First is a parallelizable like one, p-like, which means that at every positive threshold crossing, we register a count, and then the maximum signal before the subsequent negative threshold crossing is considered a measure of the energy. But in case of pileup, we will only have one threshold crossing, so one count, and we miss the second one, and also the energy measurement is distorted. Now with the other algorithm, which is non-parallelizable like or NP-like, we are still able to get two counts out of this situation. That works as follows. After the threshold crossing, a window of length tau and p starts. And at the end of that window, we evaluate if the pulse strain is still above threshold or not. And you can see here in this case, that is the case. So we start a second, or we register a second count, start a new window, and then evaluate at the end of that window again. And then in this case, we would see there is no, the signal is not above threshold anymore. But for such an algorithm to work, it's very important that the length of tau and p exceeds the time over threshold of the pulses. Otherwise, we would get two counts for a single pulse. So we carefully analyzed, let's say, the time over threshold for the highest energy pulses. And we studied two threshold values, namely 15 keV and 30 keV. And then we found these numbers. So for example, for the relatively high 30 keV threshold and the high cutoff frequency, we found a value of 45 nanoseconds, and then it ranges to 16 nanoseconds for the lower threshold and the lower cutoff frequency. Then I want to share some results with you. On the first dose obtained with the radioactive sources, on the top row, we will have the data for the 25 megahertz filter, and on the bottom row for the 100. So we first look at this pulse height spectrum for an americium-241 source, and here the 60 keV emission is of major interest, so this peak. And using a Gaussian fit, we determined an energy resolution of about 19.5% full width half max at 60 keV. And for the 100 megahertz case, as expected, this value is slightly worse, so 21.5. The question is, how does this compare to cadmium telluride or cadmium zinc telluride, for example? Well, it's at least comparable to the value that was reported for one detector that was developed for a prototype CT scanner, which had these pixel dimensions. So it's at least comparable to that. And I want to highlight that for in the next upgrade of our silicon PM, we expect that, or we basically know that the photon detection efficiency, so the efficiency by which the silicon PM detects the optical photons, will be improved by a factor 2. So that can lead to, at best, an improvement in energy resolution of √2. Now here we're going to look at a diagram that contains the spectra of all 3 radioactive sources, and that gives a kind of feeling for how well we can separate different energies from each other. And then, for example, you can see that 60 and 80 keV can be well separated, and that's still the case for the 100 megahertz filter as well. Then here we plot the pulse height as derived from these plots for each energy against each other. And then we see that the detector has a fairly proportional response, which is nice to have, of course. And then at the X-ray tube facility, we also measured under low rate conditions some X-ray tube spectra, which look like this for the 25 megahertz filter. So we see that the spectrum basically stops at a pulse height that corresponds to 120 keV. We determined this conversion based on the plot that I showed on the previous slide. So that's what you expect when you set your tube voltage to 120 keV. Then we see this gradual increase, a sign here of the characteristic X-rays from the tungsten target of the tube, and then decreasing spectral intensity towards the lower energies. And also for the 100 megahertz case, we were able to see those features. Regarding the count rate curves, I'll first show again results for the 25 megahertz filter. So the slower detector, so to say. So for non-parallelizable light counting, we observe the expected behavior. That is that the count rate curves approach asymptotic values at an output count rate that is basically equal to 1 over the value of tau and p. So in the case of the 30 keV threshold, that is 16.5 megacounts per second per pixel here. We made sure that these data points are, that the input rate at these first data points is sufficiently low so there would be no pileup, and we could say, okay, output count rate equals input count rate. And then also by realizing the tube current and input count rate are proportional to each other, we could plot this curve for ideal counting and plot an estimate of the input count rate on the top horizontal axis here. And then the curves for parallelizable light counting also show the expected behavior. So they reach a maximum value, which in the case of the 30 keV threshold is 7.5 megacounts per second per pixel. And then they approach 0 for very high rates. For the 100 megahertz, the count rate capability improves. So for parallelizable light counting, 30 keV threshold, we reach 10.5 megacounts per second per pixel now. And the curves for non-parallelizable will get as high as 22 megacounts per second per pixel. Again, the question is, how does this compare to cadmium telluride, for example? Well, that's summarized in the table that I'm going to show here. So on the left-hand side, there are the numbers for lanthanum bromide that I showed on the previous slide. And on the right-hand side, I mentioned some numbers for, let's say, the highest quality cadmium telluride, zinc telluride that was developed for diagnostic photon counting CT. And a parallelizable system, such a parallelizable system reaches a maximum observed count rate of about 30 megacounts per pixel, and the non-parallelizable like one may get to 28 megacounts per second per pixel. So we're actually quite close. So what we could do now is say, okay, this is promising. We're going to miniaturize our pixel size as well, such that we get sufficient rate capability per squared millimeter. We could also say we stick to applications that require a pixel size of only 1 by 1 millimeter. And typically those applications also have lower rate requirements. An example would be, for example, a cone beam CT on the radiotherapy gantry, where the input rates are more in the order of 10 megacounts per second per squared millimeter. Or we try to outperform the rate capability of cadmium telluride or cadmium zinc telluride by moving to even faster scintillators. An example would be the praseodymium bromide, which is still a material that's not commercially available, but can be grown by research groups. And that has a decay time of about 8 nanoseconds. So that's twice as fast as lanthanum bromide. So the conclusions of this talk, we had a look at X-ray photon counting using silicon photomultiplier based lanthanum bromide detectors. We studied energy response and count rate performance. For the energy response, we noticed that pulse height is proportional to X-ray energy and energy resolution of about 20%. And that's at least comparable to some cadmium telluride or cadmium zinc telluride detectors. And regarding the count rate performance, we found for parallelizable light counting a maximum observed count rate of 10.5 megacounts per pixel, and for non-parallelizable light rates approaching 22 megacounts per second per pixel. And also these numbers are reasonably close to the performance of the direct conversion detectors. So that makes us very confident to move on with this research. So with that, I would like to conclude this talk, and thank you for your attention, and happy to take any questions.
Thank you. Those results are very impressive. So what I'm wondering is if the energy resolution is limited by something fundamental in the material, or do you think that is something that can be improved with, for example, hardware, readout hardware, or something like that?
Thank you for your question. So the energy resolution is, for a scintillation detector, basically determined by two factors. One is the number of scintillation photons that you detect, and the other are due to a lot of other materials properties which are basically put together in a single number. And it's quite hard to improve that, basically. So, I mean, people try to, for example, make the scintillator generate more light per keV of deposited energy. That kind of research is performed. So I don't know if you consider that a hardware improvement or.
Okay, thanks. So if you would change the pixel size, if you would make smaller pixels, I guess that would degrade the energy resolution. Is that correct?
That could happen indeed. So it could be that the aspect ratio of the crystals is affecting, let's say, the light collection efficiency as a function of depth of interaction. And that can have a negative effect on energy resolution. That's true, yeah.
Thanks.
Nice work. I think I had a similar question, but I was wondering if you could speak to the challenges of making smaller pixels, smaller crystals with lanthanum bromide, or like how small could you make them?
Yeah, yeah, that's indeed like a major challenge to, like the next challenge to overcome. So in general, you can make smaller you can make smaller pixels with scintillators than what's shown here. For lanthanum bromide, this has not been done yet. We're thinking about several solutions which could be kind of growing the material in a kind of reflective matrix that you have built beforehand, such that it's basically confined within that element of the matrix. Then that could be one way to achieve this.
So the response or the output of silicon photomultiplier are usually very sensitive to temperature and bias voltage. Did you observe those? For example, the fluctuation of output versus bias voltage?
So the response of the light sensor, right?
For example, the output gain of the entire system.
Yeah, okay. So temperature and bias voltage. Yeah, so in general, I have to say, like, this silicon photomultiplier is more stable with respect to temperature changes and bias voltage than, for example, an avalanche photodiode that also produces a high gain. So, I mean, yeah, you need to control the temperature and generate a stable bias voltage, but it's not like that the gain changes a lot as a function of temperature compared to, for example, an avalanche photodiode. So
Thank you.
You mentioned a certain count rate limit on the cadmium telluride and CZT. Was that from the sensor material or from the readout chip?
That basically is for, like, let's say, the whole system. So it's including the readout chip.
Okay.
So
what readout chip are you using?
So for these numbers that are reported were found in literature by in articles written by people working at medical device companies like Philips and Siemens, who were working on prototype systems. So it includes basically their sensor material and their readout AC.
Okay, thank you.
Let's thank the speaker again.